Imagine the universe not as a vast emptiness, but as a finely woven tapestry. This tapestry, the fabric of reality itself, is composed of an intricate lattice of elastic strands. These strands, vibrating with unimaginable energy, exist at the smallest conceivable scale, the Planck scale, a realm far smaller than even an atom's nucleus. This lattice is not static. It hums with ceaseless activity, a quantum dance of energy and potential. The strands, though minuscule, possess elasticity, resisting stretching and compression. This inherent property of the lattice has profound implications for the nature of the universe, preventing the formation of infinitely dense points. Think of a stretched rubber sheet. If you place a heavy object on it, the sheet will sag under the weight. However, the sheet itself will never reach a point of infinite density. Similarly, the elastic nature of the Planck scale lattice prevents the formation of singularities, those points of infinite density predicted by classical physics. Within this vibrant lattice, particles, the building blocks of matter, emerge not as independent entities but as disturbances, ripples propagating through the interwoven strands. These disturbances, akin to waves on a pond, carry energy and momentum, the defining characteristics of particles. Picture a pebble dropped into a still pond. The impact creates ripples that spread outwards, carrying the energy of the disturbance. Similarly, within the Planck scale lattice, localized disturbances manifest as particles, their properties determined by the nature and energy of the initial perturbation. A high-energy disturbance might create a massive particle, its presence felt strongly throughout the lattice. A low-energy disturbance might manifest as a lighter particle, its influence more subtle. The diversity of particles we observe in the universe arises from the rich tapestry of possible disturbances within this fundamental lattice. Energy, the lifeblood of the universe, takes on a new meaning within the framework of the unified geometric wave theory. It's not a separate entity, but an intrinsic property of the vibrating lattice itself. The more vigorously the strands vibrate, the greater the energy density within a given region of the lattice. Mass, often considered a fundamental property of matter, emerges as a consequence of these vibrations. More complex, entangled vibrations within the lattice correspond to particles with greater mass. A simple periodic vibration might represent a light particle, while a chaotic, highly energetic vibration could correspond to a massive particle. This intimate relationship between energy and mass, woven into the very fabric of space-time, provides a deeper understanding of Einstein's famous equation, E equals mc squared. Energy and mass are not merely equivalent, they are two sides of the same coin, different manifestations of the underlying vibrations within the Planck scale lattice. Gravity, the force that shapes the cosmos, arises from the interplay between energy and the geometry of the lattice. As energy accumulates within a region of the lattice, it causes the surrounding strands to bunch slightly, creating a subtle curvature. Imagine a bowling ball placed on a trampoline. The weight of the ball causes the trampoline surface to sag downwards, creating a curvature around the ball. Similarly, the presence of energy within the Planck scale lattice causes a localized curvature, a warp in the fabric of space-time. This curvature influences the trajectories of other particles moving through the lattice. Like marbles rolling on the curved surface of the trampoline, particles are drawn towards regions of higher energy density, following the contours of the warped space-time. This, in essence, is the experience of gravity. The unified geometric wave theory goes beyond gravity, seeking to unify all forces within a single elegant framework. Electromagnetism, the force responsible for light, electricity, and magnetism, emerges not as a separate entity but as a consequence of twisting the strands of the lattice. Imagine twisting a single strand within the lattice. This twisting motion creates a disturbance that propagates along the strand, similar to a wave traveling down a rope. This propagating disturbance within the unified geometric wave theory is what we perceive as an electromagnetic wave. The direction of the twist determines the electric and magnetic field components. A clockwise twist might correspond to an electric field, while a counterclockwise twist could represent a magnetic field. These twists and their associated disturbances provide a unified description of electromagnetism, linking it directly to the geometry and dynamics of the Planck scale lattice.